Hey everybody! In this video, we're going to go over the solutions for this week's section handout on game trees and utilities. Let's start with game trees. For question 1, we're asked to run Minimax for a 2-player game. The triangle that points up here is a maximizer node, and the triangles that point down are minimizer nodes. At the root, we'll need to calculate a max over its children's values. So before we do that, we need to calculate its children's values. For this node, we take the min of its children, which are 10, 8, and 3, so the value of this node is 3. Likewise, for this node, we take the min of its children, 2, 15, and 7, so the value here is 2. For this node, we take the min of 6, 5, and 4, so the value is 4. Now, for the root, we take a max over 3, 2, and 4, and so 4 is largest, and we pick that. And 4 is the value at the root. And we're done. So now we get to alpha beta pruning. For the setup of this problem, I intentionally took away the leaf values here, since in the eyes of our computer program, it doesn't know what the values of the leaves are until we explore them. Up here is the definition of what alpha and beta symbolize. Alpha is the best value max can guarantee in some node on path to root. Likewise, beta is the best value min can guarantee in some node on path to root. What does it mean to be on path to root? Well, each node keeps around its own local alpha and beta values, so the path to root would be from the node we're currently evaluating all the way up the tree to the topmost node. So for example, if we're currently on this minimizer node, the path to root from this node would be this node plus the root node. The pruning conditions are, for a maximizer node, you prune if your current value is greater than beta, because that means that the minimizer would not let the game get down to the current max node, since the minimizer has a better option of beta, guaranteed higher up in the tree. Likewise, for a min node, you prune if your current value is less than alpha, because that means that the maximizer would not let the game get down to the current min node, since the maximizer has a better option of alpha guaranteed higher up in the tree. We start at the root and initialize alpha and beta to their worst possible values for the players, since they both can't guarantee anything if we haven't explored any parts of the tree. Hence, alpha is negative infinity and beta is positive infinity. We assume we traverse the tree from left to right, so we go down to this min node here. We also pass down the alpha values and the beta value. We explore the left child here, also passing down the alpha and the beta value. And this child is a leaf node, and the value is 10. So we propagate 10 back up to this node. This node will set its value currently to 10. Also, beta will get updated to 10, since min can now guarantee a value of 10 from this node. Can we prune? At a min node, we can prune if our value is less than alpha. But alpha right now is negative infinity, so we can't prune yet. The reasoning is that max might still want to go down to this path, since it currently doesn't know anything about its other possibilities. So we continue to explore. We go down to the next branch, and we pass alpha and beta down to this path. This path is also a leaf node, and it has a value of 8, so we propagate the 8 back up to this min node. This min node prefers the 8 over 10, so we update its value to 8, and likewise we update beta to 8. We still can't prune for the same reasons, so we keep going. We pass alpha and beta down to the final branch, and this is also a leaf node. It reveals a value of 3. We propagate the 3 back up to the min node. The new value here is 3 because that's preferred over 8, and likewise beta gets updated to 3. This min node has no more children, so we propagate the 3 back up to the max node. We temporarily set the max node's value to 3, and we also update alpha to 3, because now max can guarantee a value of 3 by going to the left branch. We can't prune at the max node because we don't satisfy the condition at the max node that v, which is equal to 3 right now, is greater than beta, which is currently infinity. Intuitively, this means that max could potentially get something better down the middle branch or the right branch, and so we need to continue exploring. Since we're going left to right, we go down the middle branch next, and we bring down the values of alpha and beta, which are 3 and positive infinity. We explore the left child next, and we bring down the values of alpha and beta. This leaf node contains a value of 2, so we propagate this value of 2 back up to the mid node, temporarily set its value equal to 2, and now let's test if we can prune. The testing condition for a min node is v less than alpha, and sure enough, 2, which is v, is less than 3, which is alpha. We can prune the rest of the branches. Why? Well, let's think about this min node. No matter what the values are down here, the value of this node can only get smaller than 2, since min wants to minimize the value. So 2 is the upper bound for this value here. But max can already guarantee a value of 3 somewhere higher in the tree, so max won't choose the action that brings us down to this min node. So we can prune all the remaining children, and those children are 15 and 7. We propagate 2 back up to the max node, and max doesn't update its value or alpha, since 3 is better. Again, we can't prune the right branch, since max could potentially find something good there, so we have to explore the right branch next. We pass down alpha and beta down to this min node here, and from the min node, we explore its left child. We pass down the values of alpha and beta, and sure enough, this is a leaf node, and the value here is 6. So we propagate 6 back up to the min node. It temporarily sets its value to 6. And now we test our pruning condition. At a min node, we test if v is less than alpha. So is 6 less than 3? No, so we can't prune. That's because max still has some hope down this branch of getting something better than his guaranteed 3 down here. So we have to keep exploring. And first we set the beta value to 6, and then we explore the middle branch. We pass down the alpha and the beta values, and this node is a leaf node and has the value 5. So 5 gets propagated up to the min node. Min prefers the 5 over the 6, so we update its value to 5. Again, we test if v is less than alpha, so is 5 less than 3? No, so we can't prune, and it's for the same reason that max still has hope. So we update the beta value to 5, and we explore the right child, passing down the alpha and the beta values. The leaf node here has a value of 4, so we propagate this up. Min prefers the value of 4 over 5, so it will update its value to 4, and it will update beta to 4. And since min has no more children, we're done. So we propagate this value of 4 back up to the root. Max likes the 4 over the current 3, so we update its value to 4, set alpha to 4, but it has no more children, so we're done. So the answer to this problem is that the leaf nodes 15 and 7 got pruned. Next is Expectimax. The min nodes on this layer now got replaced by chance nodes, where instead of taking the minimum across the children's values, we take an expectation over the values. In this problem, we assume all the branches under the chance node occur with equal probability, so we're just looking for an average. For this chance node, the average of 10, 8, and 3 is 7. For this chance node, the average of 2, 15, and 7 is 8. And for this chance node, the average of 6, 5, and 4 is 5. At the root, we take a max over 7, 8, and 5, and the value that wins is 8. So the value of the root is 8, and these are the values of the nodes after running Expectimax. So, can we prune in this game tree? Well, the answer is no, because the maximizer needs to evaluate all of the leaf nodes under a chance node to actually obtain the correct value of that chance node. For example, in this game tree, max chose the branch here, the middle branch, that gave it an expected utility of 8. However, let's assume that we replaced this leaf node of 7 with a negative 100. In this case, taking the middle branch would be really bad for the maximizer. But Max would have to explore this negative 100 leaf node to actually confirm the value at this chance node up here. Likewise, here's another example. Let's assume in the right branch, the 4 here was actually a 100. In this case, Max would really prefer going to the right. But again, we wouldn't know the value of this right chance node until we have explored all of its children. So we can't prune in this tree. The last part of this question is on non-zero sum games. Here, each of the leaf nodes have two numbers. The number on the left is player A's utility, the number on the right is player B's utility. Here, both players are trying to maximize his own utility, disregarding the other player's utility. Player A's move is represented by the upward pointing triangles here, and player B's moves are represented by the downward pointing triangles here. So let's look at the first of player B's nodes, which is here. At this node, player B wants to maximize the right number, so between 1, 3, and 5. 5 is the highest, and so we propagate 3, 5 up to this node. Likewise, for this node, between 4, 9, and 8, 9 is the highest, so we propagate 15, 9 up to this node. For this node, between 5, 10, and 12, 12 is the highest, so we propagate 4, 12 up to this node. And for player A wants to maximize the left number, so between 3, 15, and 4, 15 is the highest, so we propagate 15, 9 up to the root. And these are the values for this game tree. So can we prune in this game tree? Again, the answer is no. If we go back and consider a min node in standard minimax with the current value v, and let's suppose this node still has some possible successors that we're considering to explore, then min wants a value that's less than or equal to v. But max already can guarantee value alpha somewhere higher in the tree, so if v less than alpha holds true, then max would not let the game get down to this min node here. But we aren't guaranteed to have this behavior in non-zero sum games. It could be possible that when player B is maximizing his own utility, the action that player B picks could also be beneficial for player A. From this game tree, the 15-9 node here is a good example because player B, only trying to maximize his own utility, ended up picking the best value for player A. So we can't prune because there might be a leaf node anywhere in the tree that is good for both player A and player B. On to question 2, utilities. In this problem, we're given a utility function, u of x, and asked to compute the utilities of different outcomes and lotteries. For the first part, we're given that the utility function is 2 times x. The outcomes, which are the inputs to our utility function, are going to be real numbers. So let's start. For part A, we have the outcome 3. We put 3 as input to our utility function, and evaluating that, that's just 2 times 3, which is equal to 6. That's it for part A. For part B, we have a lottery, where 2/3 of the time we get the outcome 3, and 1/3 of the time we get the outcome 6. The utility of a lottery is going to be the expectation of the utilities of the possible outcomes. And the equation for finding the utility of a lottery is up here, in the upper right-hand corner. This says that the utility of a lottery with k different outcomes, each with its respective probability, is equal to the sum over all of the k outcomes of the probability of the outcome times the utility of the outcome. So using this equation, we can write that the utility of this lottery is equal to 2/3 times the utility of the first outcome, which is 3, plus 1/3 times the utility of the second outcome, which is 6. U of 3 is just 2 times 3. U of 6 is just 2 times 6. So simplifying this, we have 2/3 times 6 plus 1/3 times 12. That's equal to 4 plus 4, which is 8. For part C, we have the outcome -2. Putting this into our utility function, we see that u of -2 is equal to 2 times -2, which is equal to -4. That's it for part C. For part D, we have a lottery, where half the time we get an outcome of 2, and the other half the time we enter a second lottery. Inside the second lottery, half the time we get an outcome of 4, half the time we get an outcome of 6. Since we have two lotteries here, I'm going to call the outer lottery L1 and the inner lottery L2. Using the utility of a lottery equation up here, we can write that the utility of the outer lottery L1 is equal to 1/2 times the utility of the first outcome, which is 2, plus 1/2 times the utility of the second lottery. The utility of the second lottery is equal to 1/2 times the utility of the first outcome, which is 4, plus 1/2 times the utility of the second outcome, which is 6. Substituting this expression here for this u of L2, since that's equal here, we get that the utility of L1 is equal to 1/2 the utility of 2, plus 1/2 times 1/2 the utility of 4, plus 1/2 the utility of 6. If we distribute out this 1/2, we get that u of L1 is equal to 1/2 u of 2, plus 1/4 u of 4, plus 1/4 u of 6. U of 2 is just 2 times 2. U of 4 is just 2 times 4. U of 6 is just 2 times 6. So if we simplify this, we get this is equal to 1/2 times 4 plus 1/4 times 8 plus 1/4 times 12, which is equal to 2 plus 2 plus 3, which is 7. Here's another approach to this problem. I'm going to draw a picture to represent how the lotteries play out. So in the outer lottery, L1, we have a 50% chance of getting the outcome of 2, and the other half of the time, we enter the second lottery, which is L2. From L2, half the time we get the outcome of 4, and then half the time we get the outcome of 6. So we can construct this tree-like structure where we can read off that this lottery can be represented as another lottery where half the time you get a reward of 2, a quarter of the time, that is 1/2 times 1/2, you get a reward of 4, and the other quarter of the time you get the outcome of 6. So this lottery is identical to this lottery, and if you write out the utility of this lottery, you actually end up getting this line right here. For the second part, we have a different utility function, u of x equals x squared, but the same way of thinking applies as in the first part. So for part A, we have the outcome 3, so we put 3 into our utility function, and we get 3 squared, which is equal to 9. For part B, again, we have a lottery, 2/3 chance of getting the outcome 3, 1/3 chance of getting the outcome 6. So the utility of this lottery is equal to 2/3 times the utility of 3 plus 1/3 times the utility of 6. The utility of 3 is equal to 3 squared, and the utility of 6 is equal to 6 squared. Well, simplifying this, we get 2/3 times 9 plus 1/3 times 36. That's equal to 6 plus 12, and that's equal to 18. For part C, we have the outcome -2. So we put -2 in the utility function, and we get -2 squared, which is equal to 4. For part D, we have, again, this lottery here. Let's flip back to the previous part. In the second approach, we transformed this lottery into a more simpler lottery here. Let's do the same for this problem. So we can rewrite this lottery as a lottery where half the time you get the outcome of 2, a quarter of the time you get an outcome of 4, and a quarter of the time you get the outcome of 6. Well, we can write the utility of this lottery as 1/2 the utility of 2 plus 1/4 the utility of 4 plus 1/4 the utility of 6. The utility of 2 is 2 squared, the utility of 4 is 4 squared, and the utility of 6 is 6 squared. So, simplifying this, we have 1/2 times 4 plus 1/4 times 16 plus 1/4 times 36. That's equal to 2 plus 4 plus 9, which is equal to 15.